Okay. Now we'll continue our discussion of special theory of relativity. So in yesterday's class, we discussed proper time. We also discussed uh, the uh, the composition rule of velocity. That means addition of velocities in special theory of relativity, and we also seen some consequences of Lorentz transformation. That means uh, the aberration of light and Doppler shift. Okay. So now let us see what happens to momentum. Okay. So momentum in special theory of relativity. Okay. So in usual the usual definition of classical mechanics, okay, of momentum, P equal to mv, or let me write mu. Okay. And when there are no forces acting on the system, okay, if the system is isolated, okay, then we have conservation of momentum, of linear momentum. Okay. But now suppose if I take this definition and extend to relativity and say that this is my definition of momentum in relativity also. Okay. Then what we'll see is that if we use the above definition of momentum, then we will have problem with conservation principle. Okay. It is very simple to see this contradiction. Okay. If you use this definition of momentum in relativity, okay, where m is the mass and u is the velocity, okay, then you will have uh, non-conservation of momentum. Momentum will not conserve. Okay. So to see this, okay, let us go back to classical mechanics, your classical physics, non-relativistic physics, okay, and let us consider the collision of two particles. Okay. Let us suppose we have a particle MA with mass MA and MB, and for simplicity I will assume that these masses are same. Okay, but still I will write MA and MB. Okay, and let us assume, okay, so this is my particle A and this is my particle B. Okay, and they're colliding with each other. There is a head-on collision of these two particles. There is a head-on collision of these two particles. Okay, so let u be the velocity. So let us consider this frame as k prime frame. Okay, and in k prime frame, let u prime be the velocity vector of particle A. So what will be the okay? So suppose I will also give you the information that ua is minus ub. Okay, so the velocity magnitude are same, but they are in the opposite direction. That is, we are discussing the head-on collision. Okay, so for a particle A, we are in K prime system. Okay, so let us see. We have these initial conditions. Okay, you have mass Ma which is equal to mass mb, and velocity of particle A is negative of velocity of particle B. Okay. After the collision, okay, suppose this particle A goes in this direction, okay, and this particle goes in this direction. Okay. So from classical mechanics, what we can say? Okay. So before the collision, okay, the initial momentum P initial, okay, is 0, right? Because ma ua prime minus mb ub prime, but magnitude of ub is same as magnitude of ua. Okay. So initially we have 0 momentum. Okay. So what is the final momentum? Okay. So after the collision, if I break this component into x and y components, okay, ua prime and ub prime, if I break these two components into xy, these two vector in xy components, okay, and okay, so this collision is elastic collision. We are discussing the elastic collision. Collision is elastic. Okay. So ux a, okay, this is uxa, okay, this is uya, okay, this will be uxb, and so everything is prime, and this is uyb. Okay. So uxa prime, okay, is equal to, okay, because of this choice, okay, uxa prime is minus of uxb prime, okay, and uya prime is equal to minus of uyb prime. Okay. Now because these collisions are elastic, the kinetic energy is same. Okay. Kinetic energy before the collision is same as kinetic energy after the collision, and because of that, this velocity, okay, v, okay, will be same as u, only direction will be different. Okay. The magnitude of final velocity of a is same as magnitude of initial velocity of a. Okay. Obviously the direction will be different. So if I resolve this final velocity of a into two components, final velocity I will call as v. Okay. So vxa, okay, prime, because we are in k prime system. Okay. So vxa will be uxa, okay, u prime xa, then vya prime will be equal to minus of u prime ya. Okay. That means direction of this velocity of a is getting reversed. And similarly we have v prime xb, okay, v prime xb, okay. See, initially the x component of b is in this direction, so finally we will have, this is b particle, this is in this direction. Okay. So there is some problem, okay, with this notation. Okay. So vxa will be in the same direction, right? So vxa will be equal to u prime xa, that is okay. Vya will be v prime ya will be negative of u prime ya. Okay. Then v prime xb, okay, v prime xb, okay, is same as u prime xb, okay, and v prime yb is equal to minus of u prime yp. So the y component of final velocities are getting reversed. Okay, we can assume this also. This is one type of collision. You can say that this is a particle come here and goes here. Okay, then accordingly these equations are going to change. Okay, fine. So what is the final momentum? Okay, final momentum. Okay, so you have p final momentum in x direction. Okay, will be what? Final momentum in x direction is x component of a, okay, and x component of b. Okay, so x component of a, so m a, okay, x component of a, that is v prime x a, okay, plus x component of b, mb, okay, v prime xb, okay, that is the x component of final momentum. Okay, let me say it is a final momentum. Okay, what will be this? Okay, so this will be equal to ma, okay, x component is y u prime x a, okay, plus mb v prime xb. V prime xb is u prime xb. Okay, but this is negative u prime xa, okay, u prime xa is negative of u prime xb. Okay, so this is 0. Okay, and the y component, okay, the y component of final momentum will be what? Is will be again 0. Okay, because you can see from here, okay, it is ma v prime ya plus mb v prime yb. Okay, v prime ya is minus of u prime ya, and this will be minus of u prime yb, but u prime ya and u prime yb, they are negative of each other. Okay, so final momentum is also 0. Okay, hence we have the conservation of linear momentum. Is it clear? Okay, now let us, so I will just erase this, okay, and write it here. Okay, similarly, okay, so now let us consider the same collision process. This is just a statement that we are at the center of, if we are at the center of mass, then the moment of center of mass always remains 0. Okay, so now let us consider, let us see this collision in, let us consider a frame K. Okay, what is this frame K? Okay, let us consider again this collision. Okay, so our frame K prime is like center of mass frame. Now let us again, I will draw two particles, okay, A and B, and after the collision they go here. Okay, let us consider this K frame. K frame will be a frame which is moving with velocity v equal to u prime xb. That means my frame K is sitting on, uh, it is moving in such a way that its velocity is same as the x component of velocity of b, okay, before the collision. Okay, okay, so this frame will move here like this, okay, with its velocity equal to x component of velocity of initial velocity of particle b. Okay, in this frame also What is going to happen in this frame? What will be the momentum before the collision, initial momentum, and what will be the final momentum? Hmm? What will be the initial momentum? Initial momentum, okay, in this frame now, okay, will be initial moment, the momentum of particle A, okay, plus momentum of particle B. Okay, so now your momentum of particle A, okay, so we need velocities. Okay, what will let UA be the velocity of a particle as seen from this K frame? Okay, what will be this UA? Hmm? What will be this UA in terms of your primed velocities? Hmm?
Sir, it should be zero.
Huh? It should be zero.
No, sir, because
No, no.
it's moving in
This
the.
frame, it is this frame is moving in this direction. Okay. So what will be UA? You use your Galilean law of this velocity addition. Okay. U prime equal to U minus V. Hmm? Okay. So U will be equal to uh, U prime plus V. Okay. Fine. So your UA will be equal to U prime A, okay, X component. Okay. So X component plus X component of V, but V is already in X direction. Okay. So this V is basically U prime B, U prime X B by choice. Okay. But U prime X A and U prime X B, they are negative of each other. So no, no, there is some problem. So there are direction. Let us see. U prime X A. Okay. So just a minute. Let me see my notes. Hmm, just a minute. There is some sign difference which is coming. Okay, so I assume that, okay, so I assume my K frame to be a frame in which moves according to uh, is sitting on particle A. This is what I assumed. Hmm, okay. Okay, so this is correct. Hmm, this is a negative sign. Just a minute. So we are transforming from K frame to K prime frame to K frame. Okay. So transformation from K prime frame to, so from K to K prime frame we have U prime equal to U minus V. Okay. So from K to this frame it will be U prime plus V. Okay. This is correct. Okay. So this one is correct. Okay. So U prime, I'm concentrating on X component of particle A, okay, plus V. Okay, so that is uxb. Okay, so uxb, it is, why it should be 0? Okay, because it should see the twice. Okay, because according to this frame, this particle will move faster because the velocity will add. There is a sign difference only. Let me figure out what is the sign difference. Uh, no, no, I think this is 0. Yeah, correct, you are correct. This will be 0. Okay, so uax will be 0. Okay, and what will be your uxb? Okay, uxb will be equal to u prime xb plus v. Okay, so this will be equal to 2uxb prime. Okay. So your initial momentum will be p initial in x direction will be 2mb or ma, doesn't matter, u prime xb. Okay, final momentum will be what? Final momentum, okay, you have to consider now the, in this frame, okay, you have to consider the final momentum in x direction. I will come to y direction also. Okay, final momentum in x direction will be ma v x a plus m b v x b. Okay, so this is equal to what? Okay, v x a. Okay, so the final momentum. Okay, just a minute. So it is the final. There are too many symbols. Okay, final momentum after the sketching. Okay, yeah, so final momentum, so we need vxa. Okay, vxa will be v prime xa plus v. Okay, v is our relative velocity. Okay, so this is equal to v prime xa. V prime xa, okay, is negative of u prime u sorry, this is, yeah, v prime xa, okay, is negative of u prime xa, which is negative of uxb, okay, which is v. Okay, so this will be equal to minus u prime v, so it is, let me go. Okay, u prime x a. Okay, there should be a minus sign. U prime x a. So this is, so it will be twice of, so this vxa is same as this component. okay, uxa, okay, and uxb. So it will be twice of, yeah, so it will be twice of u prime xb, okay, and the final velocity of b x component b, this will be 0 because now it is like this, okay, so it will be 0, okay. So the total momentum in x direction is 0 still, okay, and total momentum in y direction, okay, so we need to consider y components, okay. So in if you consider the y components, okay, u a y, okay, will be equal to u prime a y plus y component of v will be 0, okay. So it will be u a y equal to u prime a y, u b y, for same reason u b y will be equal to u prime b y, and v a y, okay, v a y, just a minute, v a y will be equal to minus of u prime a y, they are not going to change, and v b y equal to plus of u prime a y or u prime b y. So you can put here b and b here. Maybe I can put it is better. B u prime b y. Okay. So again, the final momentum, okay, total momentum in y direction is also 0. Okay. So in both k and k, when the transform when the transformation of velocity between two frames are given by this, okay, then in both the frame you have momentum conservation, okay, in k frame as well as in k prime frame, okay. But we have seen that if this k frame is moving related to k prime in certain direction, then the transformation between the velocities are not like this, okay. There, the transformation between two frames are not like this, okay. So in that case, we need to use for u prime, okay, we need to use uh, u prime say x, we need to use u sorry ux will be u prime x minus v divided by, sorry, plus v, because now the direction of v is, we are going from k prime to k, and divided by 1 minus the transformation factor, okay, 1 plus, okay, u x prime v divided by c square, okay. So it's not simply this, but there is this factor, okay. Because of this factor now, okay, we'll see that there is no conservation of linear momentum. You can see that by doing the same, uh, you apply that addition rule for same collision process. Okay, you first consider k frame, okay, sorry, you first consider k prime frame and then transform it to k frame, okay. So what we need to do is see, just concentrate on just y component, okay. So if you concentrate on y component only, what is going to happen? Let us see what is going to happen. Let us redraw this collision process, okay. Now I am using relativistic rule for composition of velocities. Okay, so you have, okay, so let me, I have changed a bit. Okay, so I have particle, this I am calling as particle A, and this I am calling as particle B. Okay, and after the collision they will go. So this is my uh, particle A. Okay, it is coming and it is going, and this is my particle B. Okay, so I have just changed the particles. Okay, nothing will change. Okay, so in K frame, okay, now we want to see this collision process with new law of this velocity addition. Hmm? Okay, so your, let us go component by component. Okay, and let us concentrate only on y components. Okay, because that is sufficient to see the non-conservation of linear momentum. Okay, y component of momentum. Okay, so for particle A, okay, what will be your y component? Okay, you have u x a, u prime x a, u prime x b. Okay, then you have u prime y a, u prime y b. You have the center of mass frame in which these are the initial velocities of particle A and particle B in component wise, and similarly we have final velocities v prime x a, v prime x b, and v prime y a, and v prime y b. Okay, now tell me what will be initial velocity of particle A, okay, in frame K. In frame, this is in K prime frame. All these are in K prime frame. Okay, now in K frame, just tell me what will be the initial velocity of particle A, y component of initial velocity. Okay, how we are going to do? Okay, how your y comp, see the velocity is now, the K frame is what? K frame is moving like this. Okay, so what will be your velocities? How the y component of velocity will transform? It will be u prime y a, okay, divided by gamma into 1 minus, it is in relative velocity is in x direction. Okay, so it will be u a x prime v divided by c square. Okay, but u a x prime, okay, our choice of frame K is such that u prime x, u prime x component of particle A in frame K prime, okay, is matching with your relative speed. Okay, minus of relative speed, because it is in, it is sitting on this B frame. This K frame is sitting on B and it is moving with u x prime B. Okay, fine. So V is u x b. Okay, clear? Okay, so uy, okay, so because of this it will be minus, so it will be minus here. Okay, and u a x prime will be equal to, so this will be equal to minus u prime a y divided by gamma into 1 plus, okay, u x b v divided by c square, but u x b prime is same as v, so it will become v square. So I don't have to write this. So this is just v square. Similarly, y component of particle 2, that is b, will be what? Y component of particle b in prime frame divided by, okay, gamma into 1 minus, okay, vx prime b, okay, the ux prime b, that is v, then there is a v, so it will become v square by c square, okay, and that's it. Okay, so this is the y component of particle a, y component of particle b before the collision. Okay, now after the collision, what is going to happen? After the collision, your particle a, it will have these velocities, okay, and after the collision you have this resolution, okay. Before the collision, your y component of a was negative, okay. After the collision, it will become just positive. Okay, so after the collision, what is going to happen? After the collision, your VAY, okay, in unprime frame will be equal to minus of UAY in unprime frame, okay, but UAY in unprime frame is minus of this quantity in prime frame, okay, so it will be UAY, okay, prime divided by gamma into 1 plus V square by C square. Okay, and VBY will be equal to VBY. So initially we have y component along positive direction, finally it will become negative direction, so it will be minus of UBY. But what is UBY? UBY is this, so it will be minus of UB prime y divided by gamma into 1 minus v square by c square. Okay, but note that u prime ay, u prime by, okay, they are the velocities of this particle a and b, initial velocities of particle a and b in prime frame. And how we have arranged, the way we arranged our masses ma equal to mb, and velocities were in opposite direction. Okay, they're in same in magnitude and opposite in direction. So u prime ay is equal to minus of u prime by. Okay, so even if I substitute that, okay, here now you can substitute, you can either replace u prime ay or you can replace u prime by, and now you calculate the final momentum. Okay, okay, that means uay plus uby. Okay, so your initial momentum is ma uay plus mb uby, and your final momentum will be in y direction. Okay, ma uay plus mb uby. Okay, obviously you are getting completely different formulas. Is it clear? Because of these factors, okay, you are getting completely different formulas for momentum. So for example, your change in momentum, okay, in y direction will be what? Okay, your change in momentum in y direction as seen from k frame. Okay, this will be equal to your final momentum in y direction. Okay, so let us calculate change in momentum for particle A. Let us go particle wise. Okay. Change in momentum for particle A in y direction. Okay, this is equal to final momentum of A y component. Okay, final momentum of A in y direction minus initial momentum of A in y direction. Okay, so this will be equal to 2m 2ma y a u a y. Okay, if you see this, okay, final velocity is this, initial velocity is this. Okay, so change will be these factors will u prime ay minus minus plus u prime ay, and this factor will remain here. Okay, so it is, I have written in terms of, here I have written in terms of unprime coordinate. Okay, okay, but you can obviously write in prime coordinate. Okay, so in the prime coordinate it will become 2ma u prime ay divided by gamma 1 plus v square by c square. And now what is change in momentum of particle B, y component of momentum of particle B? It will be final momentum of particle y component of particle B minus initial momentum y component of initial momentum of particle B. Okay, this is equal to, you can see from here, you can see from here, final momentum will be minus of ma u prime by and this factor, okay, minus this. Okay, so it will be minus of 2 times, let me write 2 times, to minus 2 times mb u prime by divided by gamma into 1 minus v square by c square. Okay, so this is final momentum of particle B, change in y component of momentum of particle B. Okay, now you see that total change will be this plus this. Okay, but because of this opposite signs, these factors are not going to cancel. Okay, we know that u a prime y is minus of u b prime y. Okay, even if we substitute that and add them, okay, because of these signs your net momentum will be non-zero y component. Okay, this is in k frame. In k prime frame we are getting net momentum to be 0. So clearly you can see the violation of your uh, linear conservation of linear momentum. If we stick to this definition of momentum, if we stick to this definition of momentum, okay, is it clear? Okay. Because of, see, the point is the following: if you use Galilean law for adding velocities, okay, everything is okay. Okay, there is no problem. You will see the conservation. Okay, and if you use this definition of momentum, your usual definition of momentum, then according to Galilean transformation, whether you the if the momentum is conserved in one frame, then this will the momentum will conserve in any other inertial frame. Okay, but now instead of Galilean transformations, if you use the velocity transformations, okay, in special relativity, okay, then not see the conservation of linear momentum. If the momentum is conserved in one frame, it's not necessary that it will conserve in another frame if you use this definition. Okay. Now you can, by inspection, by taking into factor this factor into account, okay, we can propose the following definition of uh, relativistic momentum, relativistic 3 momentum. Okay, so suppose instead of using this relation, Okay, instead of using this relation, we will use this will be replaced by m v divided by or mu. Okay, we were using u, so let us use u. U is the particle velocity. Okay, so instead of this, if we use this quantity u square by c square, if we use this definition of momentum, okay, there is this is not v, this is u. There is no mention of v here. Okay, it's only in one frame. If we use this definition, then you can check that the momentum will conserve in our earlier example. Okay, you have four particles. Okay, then if you consider this definition of momentum, then in this collision process, whether you see it from k prime frame, that is center of mass frame, or you see from k frame, okay, it doesn't matter. Okay, your momentum, total momentum will conserve. You can see that it is just now this factor. What will happen is that this factor will come as a common factor. Okay, so all because of this factor, these factors will disappear. Okay, this factor will disappear. Okay, and you will again get the conservation of momentum. Okay, clear? So we need to change the definition of momentum in relativity. Okay, so we need to define uh, the momentum in this way. Okay, but apart from this, there is intrinsic reason why we should define the momentum like this, and that reason is the following. Okay, suppose, okay, we have these three velocities, right? Vector u, okay, that is u1, ux, uy, and uz. So there is a particle moving with velocity u. Okay, its component will be ux, uy, and uz. Okay, how we define this ux by definition is dx by dt, and so on. Instead of defining this, okay, let us consider the following. Let us consider u is this dx vector x by, say, d tau. Suppose if I define my u like this, okay, is it clear? So instead of this, okay, so let me call this as some different name. Okay, so uh, maybe that we will introduce later. Okay, but let us, okay, so let us consider this expression, okay, where d tau is your infinitesimal proper time. Okay, so what will be ux? Okay, so let us introduce so ux will be dx by d tau, the x component of vector x, that is x, that is dx by d tau. And what is d tau? D tau was, okay, gamma dt, right? D tau was gamma dt, right? Am I correct in assuming that d tau was gamma? It is 1 over gamma, I think. Yeah, it is 1 over gamma. So d tau is 1 over gamma dt. Okay, so if you substitute it here, you will get gamma dx by dt, that is gamma your earlier ux. So let me call this as some tilde. Okay, let me call this as some tilde. Let me denote it by tilde. Okay, so this is equal to your ux. What will be your u tilde y? U tilde y will be dy by d tau. Okay. This will be gamma dy by dt. It is gamma uy. Okay, and u tilde z will be same as gamma uz. Okay, suppose if I define the new velocities in terms of proper time. Okay, and remember what is proper time? It is the time measured by, suppose there is a particle moving. Okay, then you assign a clock with that particle, and the time interval shown by that clock is your data. So if it moves infinitesimally on this curve, okay, then the proper time will be data. The time recorded by this observer will be d tau. That d tau is your proper time. Hmm? So, as mentioned earlier, this proper time is the time measured by co-moving observer, which moves with the particle. The observer which moves with the particle. Hmm? So, if I use the proper time, if I define the velocity through proper time, then we have these relations. Okay. Now, what will be will show later on that these three numbers, along with, now since this is a proper time, I can also define the following quantity. Suppose if I define the following quantity, say u0, okay, as, or ut, let me say ut, as, instead of x you just write dt and construct this differential dt by d tau. What will be dt by d tau? Okay, dt by d tau will be just 1 over gamma. Okay, dt by d tau will be dt by gamma dt, so it will be gamma. Okay, so ut tilde, ux tilde, uy tilde, uz tilde, if these four numbers, if I assemble these four numbers in the following way, ut tilde, ux tilde, uy tilde, and uz tilde, these four numbers, okay, transform in a same way. Okay, suppose if I take this four number and go to another frame, then I have prime frame here. Okay, then the transformation between unprimed variables and prime variable will be this. This matrix is your same Lorentz transformation matrix. Okay, right? Hence, the quantity u tilde, okay, which is now defined as ut ux uz, okay, transform in the same way as your coordinate vector. Okay, so your space-time event is characterized by this coordinate vector, right? So x will be t x1 x y z. Okay, the way this transform, in a similar way this will also transform. Okay, so in fact we should introduce this first and then discuss the four momentum later on, the definition of momentum after this. Okay, but conventionally we first emphasize that in relativity momentum need to be changed, okay, because it's not conserved. Okay, so the way we change the momentum is like this. Okay, this is the new definition of momentum. Okay,
Sir,
this can be this we can also convince ourselves why we are getting this definition through this. Okay, you define first four quantities
sir,
which transform in the same way as your coordinates. Yes, yes, there is a question.
sir, what this ut tilde define?
We
What
will
does
see
it
later
signify? dt by d
what
tau.
no, we'll see that what it defines, what it gives us. Okay, we will see later. Okay, I can construct that quantity. That is the whole point.
And
We'll
sir,
see
in
what
that
is. Hmm? We'll see later on
in
what
the
is the
Unix
meaning of that.
filter type definition, we have taken
Hmm? Go on.
dx upon d tau.
Yes.
Okay,
Hmm.
so why don't we change the dx? Why we take the dx same in both cases, dx upon dt and dx upon d tau?
No, what?
Why we don't change the dx and dx
No,
prime?
no. See, I want something like velocities. Okay, this has the dimension of time. Okay, fine. Okay, so I have particle moving along this curve. Okay, it will have x y z coordinates. Okay, how these coordinates are going to change, okay, related to frame k. Okay, this is our this the dx by dt will be the velocity of this particle in frame k, instantaneous velocity you can say. Okay, now I am saying construct these quantities. Okay, construct these quantities. There is an advantage of dealing with these quantities over your ordinary velocities. The advantage is that they transform in the same way as your coordinate vector under Lorentz transformation. Hmm? Okay, and through this now we can define the momentum. We can define now three momentum as m times u tilde. Okay, fine. So it will match with this. Okay, but we'll come to this. Okay, I need to introduce some certain notations and certain algebra we need to do. Okay, why these why these quantities transform, why these quantities transform in the same way as your coordinate vector. Okay, we have to see that. Hmm? Okay, so at this moment we define relativistic momentum to be m gamma ordinary 3 velocity. Okay, clear? Okay, fine. So now interestingly, what will be once you define this, let me erase this. This is not a use. Okay, let me keep it. No harm in keeping it. Okay. So if you consider vector p, this new vector, new momentum, vector p dot vector p, what will be the out product? Okay, what will be the product of this p dot p? Just takes your usual dot product. Okay, so it will be m square, okay, u square divided by 1 minus u square by c square. Okay, now note that 1 minus 1 divided by 1 minus u square by c square minus u square by c square, okay, divided by 1 minus u square by c square is just 1. Okay, this quantity. Okay. By simple algebra, you can see that this quantity is just unity. Okay, clear? Hence, here, if I multiply by m here, okay, what I'm going to get? M, if I will multiply by m and not only m. So what I want? So let us multiply by m square c to the power 4. Okay, let us multiply by m square c to the power 4 to this relation. So I will get in from first term I will get m square c to the power 4 1 minus u square by c square, okay, minus m square c to the power 4 c square, so it will be m square c square u square divided by 1 minus u square by c square equal to m square c to the power 4. Okay, now this is equal to what? Okay, so this is, now I can write this as mc square. So okay, let me write this, the last equation, in a following way: mc square its square divided by square root of 1 minus u square by c square its square is equal to minus, there was a minus sign, right? Minus, okay, m square c square u square. Okay, with this, okay, it will be c square p square, right? So it is p dot p is just p square. Okay, p dot p is just vector p square, that is just p square. So it is c square p square, okay, equal to m square c to the power 4. So I have mc square its square divided by 1 minus square root of divided by square root of 1 minus v square by c square square minus p square c square equal to m square c to the power 4. Okay, is it clear? Okay, and this is nothing but, now you can identify, this is your energy, e square minus, so e square equal to p square c square plus m square c to the power 4. So this is your famous energy momentum relation. Okay, so here p is your vector, p is okay. So what is the motivation behind this? See, in terms of space-time coordinates, we have seen that this quantity ds square, which is equal to dt square c square dt square minus vector dx square, this quantity is invariant. So if we go from one frame to another, this quantity is not going to change. Similarly, if I construct this quantity e square minus p square c square, this quantity is m square c to the power 4. Okay, this quantity is not going to change. So this quantity is invariant quantity. Okay, this is not going to change because this is invariant quantity. Okay, in some textbook they write m as a function of v, and instead of defining p as gamma m u, okay, they define p as m u and u, okay, and they keep this mass variable, but that is actually not the case. It's not the correct way of understanding. Okay, mass is not going to change. Mass is your intrinsic property. Okay, mass, charge, spin, in fact, is your intrinsic property of particles that are not going to change. All the kinematic properties of the particles are going to change if once we go from one frame to another. And indeed, momentum is your kinematic property. So this is another invariant quantity. So this quantity remains unchanged when we go from one frame to another. Okay, fine. So this is very basic rudimentary discussion of special relativity. Okay, now to proceed further, we need to introduce certain notations and certain concepts. Okay, okay, to simplify the discussion further. Okay, and one of these concept is which we will be using is tensors. Okay, so I will uh, stop for 2 minutes. If you have any doubts, you can ask. Okay, and after that I will continue with the tensor. I will introduce tensor.
Sir,
Hmm.
sir, you said that mass is an intrinsic property. By that you meant rest mass, right?
Yeah, rest that is the mass. Is no such normally when we discuss related through invariants. Okay, we don't bother about m moving mass, rest mass. It is always it is understood as a rest mass. Okay.
Yes, sir.
सर मी थोडासा उशिरा जॉईन झालो होतो. मला पेज 2 फक्त दाखवाल का? मी एकदा स्क्रीनशॉट काढून घेतो.
But it is anyway it is recorded, right?
सर 2018 ची बॅच आहे तो याचा ऍक्सेस नाहीये.
Okay.
थँक्यू. आणि पेज 4 दाखवू शकाल? ओके सर, थँक्यू.
Sir,
Yes.
Sir,
today's part is also from J.D. Jackson.
It is J.D. Jackson. It is from there are elementary relativity books. Okay, I will use J.D. Jackson, but this is not from J.D. Jackson. Okay,
Yes.
there is a book by Resnick. Okay, a special theory of relativity by Resnick. Okay, you can use that. Okay.
sir, as you said,
Yes.
the mass is intrinsic in this case. So how we can explain the like the disintegration of nucleus type things, or the conversion of mass energy in by this method? If we don't vary the mass.
You can obviously you can do, right? So your mass energy, this in fact this relation tells you that your this relation, this is what the content of this relation is. Okay, you have mass here. Okay, your momentum and your energy. Okay. What do I mean by intrinsic property is the following: when I go from one frame to another, this quantity which is coming here, okay, this quantity is which is coming on the right side of this equation is invariant, is not going to change. Okay, that is what do I mean by mass is invariant quantity, intrinsic property. Okay, when you consider disintegration and all these, okay, obviously you can use this equation for that. Okay, but there is disintegration is different process, right? You have one particle and it is disintegrated into two. It is not in contradiction with this relation. Okay, right? Mass is the intrinsic property. You can always have it. It means that your energy mass. This is your energy mass. You can convert mass into energy. That is different point. Okay, What we are seeing here is when we go from one frame to another, this quantity is not going to change. Like, so your t changes, right? T goes to t prime. This is something else. You can write t prime in terms of t. Similarly, your mass is not such a thing. Okay. Fine. Suppose if you have 2 kilo, okay, at rest, it will remain 2 kilo at rest. Okay, it's not going to change. Even if you are moving, okay, the observer in that frame will measure 2 kilo. That's it. Okay. In some text, still in some, there is no harm in doing, in writing C. It is just a matter of convention. Okay. Instead of writing P equal to gamma mu, you absorb this gamma into M. Okay. Here, this here mu will be M times gamma. Can you call this as a variable mass? Okay. But we achieve nothing by saying that. Okay. When we say this, we have one invariant quantity. Okay. So in this definition, P is going to change, E is going to change in such a way that this quantity remains same. Okay. Fine. So you have class at 2:30, right?
Sir, the zero rest mass.
Zero rest mass. What?
The zero rest mass of photon, is it related to the STR or something different concept?
No, no. The point is that you cannot find a rest frame from photon, rest frame for photon. Forget about zero rest mass for photon. You, for photon, for electromagnetic wave, the point is that you cannot find a frame, okay, in which the photon is at rest. For all material particles, you can find a frame in which that particle is at rest. But for a photon, you cannot find a frame. Lawrence, you cannot find you cannot find inertial frame in which the photon is at rest. That is the correct statement. It's not a zero rest mass. Okay, it is the point is you cannot find the frame in which photon is at rest. So there is no point in talking about uh, rest mass of photon. It's not defined. Is it clear? Okay, so now, okay, we'll do a digression for next couple of lectures, or we'll do the digression and discuss tensors. Okay. So before discussing tensors, okay, it is just a generalization of your vectors. Okay, but there are some differences. Okay. Before discussing tensor, I need to discuss some transformation laws of your vector. Okay. So now I hope you are familiar with vector spaces and so on. Okay, linear vector spaces. Okay, because I am going to use that. Okay, now. Okay, so so suppose we have a vector space V. Okay, and let us consider I supply a basis to it, say E1, E2. Let us consider V to be dimension of V is 3, for example. Okay, then I supply basis E1, E2, and E3 to it. Okay, so I have a vector space and I have a basis. I have a given basis. It means that any vector, say, if any vector small v, if it belongs to this vector space, it means that any vector you can write as a linear combination of E1, E2 and E3. Okay, so let me write that linear combination as this: Vi, Ei, small I. Okay, these are the component of your vector. Okay, so I will write that later. Okay, these Vi's are component of this vector in this basis. Okay, in the basis E1, E2, E3. Okay, let me say that this basis is, say, B. Okay, okay, this basis set is denoted by B. Then any vector V in this capital V can be written as a linear combination of E1, E2, E3. So I goes from 1 to 3. Okay, fine. Now, for any vector space, at least for finite dimensional vector space, okay, we can define a map. Okay, let us define a map, okay, which takes me from V, okay, this vector space V, to the field over which it is defined. Okay, you know that for a vector space you require field. Okay, so let us consider a map which takes me from vector space V to this field F. Okay, so in our, if my V is R3, your three-dimensional real space, then my F, this field will be field of real numbers. Okay, let us define this map. How I define this map? This map is linear. Okay, by that what I mean, F acting on alpha V1 plus V2. Alpha is a member of this field. Alpha is some real. Okay, so if you are in confusion, assume that V is R3. Okay, so alpha is just a real number. So it is defined like this: F alpha F V1 plus F V2. So this is what do I mean by linearity. Okay, so this map is a linear map on V, and it gives me, so if I feed a vector to F, I will get a number. Okay, if I feed a vector to it, okay, I will get a number. Okay, this is what do I mean by map from V to F. Okay, and now I will consider collection of all such a maps from V to, I will use R. Okay, V to R. Okay, this collection, that means you have F1, F2, F3, so on. Okay, there's a collection of all such apes. Collection of all such maps also forms a vector space. Okay, collection of all such apes also form a vector space, and that vector space is called dual space of V. Okay, so you have original vector space V, you define a map, you define a linear map. Okay, consider collection of all such a maps. That collection is a vector space. Okay, that collection is a vector space, and that vector space is called dual space of V. Okay, and it is denoted by V star. Okay, so for example, I can define the following map. Okay, so I can define, suppose if I consider, let us consider a basis vector e1. Okay, I define a dual vector. Okay, so by the way, these members of this v star, okay, that means f1, f2, f3, all these linear maps, they are called dual vectors. Okay, so let us consider some dual vector, okay, in this v star. Okay, and how I define it? Okay, I define it in a following way: e1, okay, acting on ei is 1 if I equal to 1 and 0 if I is not equal to 1. Okay, fine. I define this dual vector in this way. Okay, so when e1 acts on ei, it gives me 1 when I equal to 1. Okay, in other words, if I consider ei and if I consider ej, then I will get delta ij. I hope you know these linear functionals. Has it been covered in MMP1? When you discussed vector spaces, the linear functional, has it been covered? Yes or no? Hello? No. Internet. Hello? I think meeting is
Sir, we did linear transformations, but functionals was not.
functional is not covered.
No, sir.
Okay. Okay. So anyway, so okay. So linear functional, the linear transformation takes you when it acts on vector space, it gives me a vector space. Okay. Linear operators. Linear functional is simpler than that. It takes vector space to real number. It takes element from vector space and it gives me a real number. Okay. Exactly, it's very simple than your linear transformation, the linear operators. Okay, fine. So I will give some examples. Okay, so I can define for each corresponding to each basis vector e1, e2, e3. I will define dual vectors where one is now written in as a superscript. Okay, here. Okay, one is this, your index on dual vector is denoted, this is downstairs, this is upstairs. Okay, this is subscript, superscript. Okay, once I define this, okay, then the action of ei, action of ei on any vector, say v, belongs to capital V, will be what? Okay, ei, any vector can be written as a linear combination of, but I need to use different index, vj, ej. Any vector can be written as a linear combination of basis vectors. Okay, And this map, this how dual vector operation, how should we perform this operation? This is sum. Okay, these are scalars. Okay, so when I add them, because of linearity, they will come out. So it will be sum or j, vj, okay, ei acts on ej. Okay, so I will get summation over j, vj, okay, delta ij. Okay, and it is nothing but vi. So the job of this dual vector ei, okay, is to pick ith component of vector v. Okay, so I define three dual vectors corresponding to three basis vector e1, e2, e3. Okay, I define three dual vectors e1, e2, e3. And what is their role? Their role is to pick out corresponding component of vector when they are acted. Say for example, if e1 is, if v is acted upon e1, then I will get v1. Okay, if e2 is acting on v, I will get v2, and so on. Okay, remember v1, v2, these components are just real numbers. Okay, if this is the basis for v, which we are assuming, then this is also a basis for v star, that I will call as b star. Okay, so it's called dual basis. Okay, you can imagine several other operations, okay, of dual vector, of linear map. Okay, so given a basis for v, I will have a unique basis corresponding to v. Okay, because of this definition, okay, we will have a unique basis corresponding to b star, unique basis corresponding to b, that I am calling as b star. Okay, yes. See, the simplest example of your dual vectors is if you represent vector. I'm just giving you the example roughly. If you represent vector by a column, okay, then your dual vector to this is just row. So that when you do this matrix, usual matrix multiplication, you will get a number. X square plus y square plus z square is just a number. Okay, but that is the case when we define inner product on this. Okay, clear? Okay. It's not difficult to imagine any linear map. Okay, so we have corresponding to every vector space, at least finite dimensional vector space, you have a dual vector space. Okay, so if your vector space is v, then it come with its dual. It always come with its dual. It's just that in ordinary space you don't realize the difference between v and v star, because you have already the inner product defined for you. Okay, so you don't realize the difference between v and v star, but when you take v, there is a dual to it, v star. Okay,
Yes. So, sir, I mean, for mapping from vector space V to a field F, we essentially need a dual vector space V star, right?
yes, this is how the dual vector space is. See, first you define linear map, which we will call as a linear functional. What is the role of that linear map? It takes me, uh, uh, it takes vector and gives me some number. Okay, then you consider collection of them. Okay, you consider collection of all such a linear maps acting on all vectors. Okay, they themselves form a vector space. Okay, what do I mean by that? If you consider any two element, any three element, then they are associative. Okay, addition of f and g, okay, is another linear functional. Okay, there exists well-defined inverse for it, and so on. So all these vector space axioms will be satisfied for this. For that, you need to use these definitions. This definition of linearity. Okay.
Okay, sir.
Right. So if you have f1 and f2 two linear functional, then you define f1 plus f2 acting on v, okay, as f1 acting on v plus f2 acting on v. Okay. So if this is a linear functional and this is a linear functional, then the right hand side is a number. So this is also linear functional. Remember here, okay, when we talk about this relation, this addition, okay, is the addition in V, because we have two vectors V1 and V2. Okay. On the other hand, this addition on the right hand side here, okay, it is in F, because this is number, this is number, this is number. So you are adding two numbers. That is the addition in field F, and this is the addition in V. Okay, so you have to be careful. Okay, similarly here it is the addition in V star, which is same as addition in V, and this is the addition in F. Okay, clear? Now,
Yes.
now once we have this dual space, okay, we can do several things. Okay, for example, okay, so when I say that this V star is a basis for uh, uh, vector space, what do I mean? This B star is a basis for dual space. Okay, what do I mean by that? Okay, let us consider any arbitrary linear functional or linear map. Sometime I will use linear functional, or sometime I will use linear map, and let us act on any arbitrary vector B. Okay, so this is equal to f acting on summation over I vi ei. Okay, but since this is a linear map, I will have vi f acting on ei. Okay. Hmm? This I will denote this number. This I will denote by say fi. Okay, because it will obviously depend on what basis vector I am considering. So this I will come here. Okay, this is just a definition. F acting on ei is fi. Okay, so this is equal to summation or I vi fi. Okay, yeah. Now you use this. Okay, and suppose if we consider the following expansion, suppose if I consider the following thing, suppose if I consider sum over j, if j, I will take these numbers, okay, fj ej. Okay, let us see what we get. Okay, then action of this, okay, suppose if I form this quantity, and if I act this on v, what I'm going to get? Okay, at this moment I am not assuming that these fj's are same as these f's. Okay, let us take some fj. Actually they are same, but I need to show that. Okay, let us form this quantity. Okay? Let us form this linear combination. Okay, fj ej, and add that on v. what we are going to get? Summation over j, okay, fj ej, then v will be summation over I, vi ei. Okay, clear? Now I will have summation over j, summation over I, okay, fi. Since now this is your linear, ej is your linear map, okay, it will act on this linearly. So vi, so this is fj, vi will come out, and I will have ej acting on ei. Okay, but what is this? This quantity is your chronicle delta. This, okay. So one sum will go, okay, one summation is going to disappear, and we left with you can choose which summation to move. Okay, you'll left with fi vi. Okay, so acting f on v is same as acting this on v. Okay, clear? Acting f on v is same as acting this linear combination on v. Okay, so whatever these numbers are, they will be same as these numbers. Okay.
Yes, sir. Okay.
Okay, so your f can be written as your any arbitrary linear functional can be written as linear combination of basis vectors. Okay, that's why we actually call these EIs are bases. They are linearly independent and they should span any functional can be written as linear combination of these basis functions. Okay. Just a minute. Okay. So now next thing is what? Okay, given a vector space V, okay, we have vector space V, okay, and suppose if I give you some basis set B, okay, and let V be the any vector in this vector space, okay, then what are the coordinate of vector V relative to basis B? Coordinate. Okay, to find the coordinate is a column matrix. Okay, how to fix these entries? Okay, since basis is given, you can express this vector as a linear combination of these basis vectors. Okay, you take these quantities v1, v2, v3, etc. Okay, and arrange in the same sequence v1, v2, vn. In general, it is vn. Okay, so this is your coordinate vector of v, vector v in basis B. So obviously, if I change my basis, these numbers are going to change. Okay, clear? So how they are going to change? Okay. Suppose my basis, okay, suppose my basis, I have a B prime basis and I have B basis. So if I go from B to B prime, okay, the question is how these components are going to change. Okay, so suppose E, see, take any basis vector in B prime. Let us consider E1 prime. Okay, this basis vector is a arbitrary vector as far as basis B is concerned. Okay, because this basis is for V, this basis is also for V. Okay, so first of all, these are the elements, these E1 prime, E2 prime, E3 prime, they are the elements of this capital V. Okay, any element in V can be expressed as a linear combination of vectors in V. That means any E prime, that is say E1 prime, can be expressed as a linear combination of E1, E2, E3. Okay, so let that linear combination be A1 1 E1 plus A2 1 E1 plus A3 1 E1, sorry, E2 and A3 1 E3. Okay, clear? So I express this as a linear combination. Okay, E1 prime as a linear combination of E1, E2, E3. Okay, then coordinate of E1 prime in the basis B is what? These coefficients, right? It is A11, A21, A31. Okay, then similarly I will have E2 prime. E2 prime will be what? E1 2 E1 hat plus A2 2 E2 hat plus A3 2 E3 hat. Okay, so the coordinate of E2 prime in basis B will be what? A12, A22, A33, and so on. You can keep on doing this. Okay, so what we'll get? We'll get at the end, we'll get the following relation: EI prime is equal to AJI E AJI EJ sum over J. Okay, clear? Remember, this first index on A is summed over. This I will choose slightly different convention which will be useful in our relativity. Okay, I will write this as, the meaning is same. I will write this as A J I. Okay, EJ. Okay, so this J is summed over. Okay, so remember, for basis, for change of basis, this first index of A is summed over. Okay, so given this, we need to find how the component of any given vector transform. Okay, so let V be a vector. Okay, in capital V. So on one hand, I can express this as VI EI. Okay, in basis B, but the same vector I can express in basis B prime, right? So it will be, let V prime I be the components of that vector in basis, uh, in prime basis. Okay, now we need to find the relationship between V prime and V prime I and VI. Okay, so how we are going to find? So this is equal to, just substitute the expression for EI prime. Okay, so it will be V prime I. Okay, EI prime is this. Okay, so it will be summation over J A J. Okay, so summation A J I. Okay, EJ. Okay, then this is equal to summation, I will alter I and j summations. Okay, so summation over j, summation over I, v prime I, a j I. Okay, e prime e cap j. Okay, and this is equal to, since I is summed over, in place of I can always use j also, means this is same as this, right? Because j, this I is summed over, I can use any index now. Okay, whether you use I, whether you use j, whether you use k, it doesn't matter. Okay, because it is summed over. So v equal to this, that is nothing but this, is equal to this. Okay, but these are basis vectors. Okay, fine, they are linearly independent. So this implies that vj equal to summation over I, v prime I, a j I. Okay, so in other words, it is equal to summation over I, a j I, v prime j. Okay, clear? Okay. So in terms of matrix, what it will be? Okay, so matrix V, okay, or coordinate of V in basis B, okay, is equal to this matrix A, okay, and coordinate of V in basis B prime. Okay, in other words, your coordinate of V in basis B prime is equal to A inverse, okay, and coordinate of V in basis B. Okay, this implies that V prime, coordinate of V in basis B prime, they are denoted by V prime 1, V prime 2, V prime 3, etc. So hence V prime I is equal to A inverse, okay, A inverse V prime I will be equal to, there's some mistake here. There's some mistake. Vj equal to this summation. There should be I here. Okay, there should be I. V prime I. I is summed over. Okay. So V prime I will be equal to A inverse I j Vj. Okay. So when basis transform like this, your components transform like this. Okay. Is it clear? When your basis transform like this, then your component transforms like this. So they transform in opposite way, so that your vector should remain fixed, should remain same. Okay, because we are seeing one and the same vector from two frames. Okay, so vector as its nature, it will remain same. Okay, we are seeing that from one frame and then from another frame. Okay, clear? So now I will, usually we don't use inverse for component. Okay, so instead of saying this as my matrix A, okay, I will denote this by A inverse, then here it will become A. Right? If I denote this by A inverse Ji, then here I will get A Ij. Okay, but that I will do later on. Okay, so this is how your vector transform, this is how your basis transform under your change of basis, and this is how the component of your vector transform.
सर तिथे
Now
VI
the
पाहिजे.
question, where
बॉक्स मध्ये.
No, here why we are? No, it is sum over j. This is sum over j. V prime I equal to A inverse Ij Vj. Okay. Is it clear? Okay. Fine. Okay. So now given this, okay, now we need to determine how, given the change of basis in on for a vector space, okay, given the change of basis for prime basis and unprime basis, okay, can we find, okay, relationship between dual basis ei prime and relationship between prime dual basis and unprime dual basis. If we know this, then we will know how the suppose, okay, so now I will denote dual vector by writing tilde here. Okay, so any dual vector, okay, you can write as we discussed before, vi v vi ei, okay, summation of I. If I know how this, what is the transformation induced on this dual basis, then I know the transformation on these components of dual vector. Okay, but that we will do in the next class. I think I should stop here because you have class at 2:30. Okay, so I'll stop here. In the next class we will continue with this discussion, and next two lecture will be devoted to tensor, and then we will again come back to relativity. Okay, fine. So we'll stop here. So our next job is to find the transformation of components of dual vector. Okay, given the change of basis in V. Okay, fine. So I will stop here. Okay. And I will let you know when we will have the timing about the next class. Okay, fine. So I will end the meeting, end the recording